Hello my dear friends and students. Dr. Muhammad Parvez here. In the last three tutorials, you have been familiarized with preliminary treatment of the protein and ligands. In this session, I am going to show you how to set up the grid box and create grid parameter file with extension GPF step by step. I shall be following 5 steps in completing this tutorial. Step 1 is about the setting of the grid around the entire protein when the exact location of the active site and the receptor is not known. Here I shall be including the ligand and the grid inside the protein space for localized docking. Here you will learn how to identify the exact coordinates of the ligand inside the protein space with the help of Discovery Studio Visualizer. In step 4, you will learn the method for calculating the exact coordinates of the active site with the help of Discovery Studio Visualizer. Here we will be generating the grid parameter file with GPF extension. Setting the grid for blind docking. Before going to generating grid parameter files, let me show what are the grid parameters. The grid parameter specifies the parameter for generating the atomic affinity maps and the PDB Qt file for the receptor. This is the 3D space inside the protein receptor where the ligand will bind for docking. It includes the size of the grid box, likewise XYZ dimension, with a spacing of from 0.1 to 1 angstrom between the grid points, and the grid box center like the X, Y and Z. What is a grid parameter file? Running the AutoGrid 4 will generate grid parameter file that will contain information on the location of grid inside the protein space where the ligand will interact with amino acid residue of the receptor. For different situations, you will need to adopt different strategies. Likewise, when the co-crystal ligand is not present with your research protein and you don't know the exact location of the active site, then you should perform blind docking. Here I am going to continue from the last tutorial of this series. First of all, you will need to open your charged protein. This is your charged protein. Go to grid and click on grid box. This will open the grid. Now cover the entire protein within this grid box by increasing the dimension and changing the coordinate of the grid with the help of these controls. The 3D coordinates and the grid size can be changed by using the different controls. The size of the grid can be changed by adjusting these controls. You can see that by changing these values, the size of the grid changes. You can also change the size of the grid by right clicking and entering the specific size and dimension. Like you can click here, instead of this 60 you can change this into 80. You can see the value changed to 80. Similarly, right here 75. OK, the grid size increased. The 3D coordinate of the grid can be changed by adjusting these controls. You can change spacing of the docking area from this control. This is the spacing. Now I am going to cover the entire protein within this grid box by increasing the dimension and changing the coordinates of the grid with the help of these controls. So first of all, I am going to increase the dimension. (126) is the maximum dimension. You can see that some residues are outside the grid. You can enclose these residues by increasing the space. To move this grid, I am going to change it from here. You can see that each control is responsible for different dimension. After this activity is done, the most important step is to save the grid coordinates. To save the grid coordinates, close saving current. The grid coordinates are now saved. If you forgot to save the grid coordinates, you will need to perform these steps again. For your record, you can also save the grid parameters and the text file. To save the grid parameters and the text file, open the grid again. The coordinates are the same as we have already saved. Go to File menu and click on Output Grid Dimension file. Give it a suitable name. I am going to give it the name of grid with extension txt. Press save and the parameters will be saved to your working directory. If you have already identified the grid attributes from elsewhere and you know the exact location of the active site, then you should fix the box on that particular area of the protein by entering the X, Y, Z values into the grid box. In case the exact coordinates of the active site are not known, then you should perform localized docking. To perform localized docking, I am going to load the co-crystal ligand that I had saved separately in PDBQT format. Go to ligand input and open. Here you can click on this lig pdbqt and press open. You can see that the loaded ligand exactly fixed in the active site. Remember that only the co-crystal ligand will go and occupy this active site. To set the grid over this ligand, open the grid. As you know that we had fixed this grid on the entire protein in this session. So these coordinates have been saved. So I'm going to reduce the size of this grid. Now go and fix the grid locally by enclosing the ligand only within this grid box. Let me check from all sides. A ligand is not enclosed yet. Check again. You can see that the ligand has now been enclosed in this grid. You can increase or decrease the dimensions of the grid according to the size of ligand and the active site. You can also change the spacing. As I have accurately centered the grid box over the ligand, I am going to save these coordinates. Go and click on close saving current. These coordinates now have been saved. You can also save the current coordinates in the text file by reopening the grid box, opening to file menu, output grid dimension file, and as we have already one file with the name of grid, let me save the current coordinates and that file again, grid dot txt, and save. You will be asked that grid text already exists. Do you want to replace it? Click on yes. So the current coordinates now have been saved to this text file. The exact location of docking site can be identified from the active site amino acid residue of protein. These information are given in literature. However, amino acid residues of the active site can also be identified by using the Discovery Studio visualizer. If you have not installed Discovery Studio Visualizer, I shall suggest install it. Soon I shall be preparing a detailed tutorial on Discovery Studio Visualizers. To visualize the active site amino acid residues of your protein, go and open the structure of the protein that you saved without deleting the co-crystal ligand. Remember, this file contains the co-crystal ligand in association with our research protein. Press open. This is the structure of our research protein. You can see that the co-crystal ligand is present with this protein structure, this one in the yellow highlight. This is the R93 ligand which is associated with this protein. Now on the interface, go to script, this menu, script. In script menu, go down to ligand interaction and then click on show ligand binding site atoms. You can see here that these are the amino acid of the active site. Now go to structure, then labels, and press add. You have options. Here you can select amino acid and then press OK. This will display the code of all the amino acid around this ligand. Open an Excel sheet, click on the amino acid of the active site, note the code of the amino acid in the Excel sheet. I am going to note this ILE115. This is the code of this amino acid. Now again go to Discovery Studio Visualizer. I shall suggest to press delete button to delete this amino acid which you have entered into the Excel sheet. Now press another amino acid, enter this name into the Excel sheet. This is valine 81. Repeat this process for each amino acid in the active site of this ligand. Delete this amino acid also, valine 81, which is highlighted in yellow. Click on another one and enter the code into the Excel sheet. I have prepared the list of the amino acid for you to show you. These are 18 amino acids present in the active site of this protein. Amino acid residues and code. You can arrange them according to the code. This first is valine, but the number is 13. The second is leucine, but the number in chain is 20. Then 21, 26, 30, 31. You can arrange them in this sequence. Deleting the registered amino acid, this will help you to avoid the duplication or to ensure the entry of all amino acid deleted the label of each amino acid once the code is saved to the Excel sheet. Now go and expand the amino acid chain in the AutoDock tool. And highlight each amino acid residues that you have registered in the Excel sheet. Likewise, the first amino acid is valine 30. This can be highlighted valine 30. You can see here. This can be highlighted by clicking in the circle in front of each amino acid that you have registered. You can see that one amino acid has been highlighted here. Now again go to the second amino acid. The second amino acid is leucine 20. Leucine 20 here. This is leucine 20. You can see that leucine 20 has also been highlighted here. Go to the next, glycine 21. This is glycine 21. You will remember that this protein is composed of two chains, chain A and chain B. You will see some amino acid that the code of that amino acid is missing in this list. Likewise, I am going to show you. Valine 81, let me highlight it. You can see that this amino acid is present in this list, but when you will check it in this dashboard, valine 81 will not be available here. You can see that here 81 is leucine, not valine. It's mean that this amino acid is not the part of this chain A. So to search valine 81, contract this chain A, expand chain B, go to 81 amino acid, here in chain B you can see that valine 81 is available in chain B. You can also click in this circle to highlight it. Look at this. This amino acid is now highlighted in the active site. You can repeat these steps for all amino acid. I have done these steps for you, and you can see that all the active site amino acid residues are highlighted in this particular area of the protein. Now I will fix the grid box over this entire area of the highlighted amino acid residues. Open the grid and repeat all the steps that we have already performed for localized docking. you can move this grid accordingly. Including all these active amino acid residues by increasing this spacing or size. Okay, now you have enclosed all the amino acid residues that were highlighted. Repeat the process of close saving current. Also repeat the saving of the coordinates in the text file. In step 3, we had identified the exact coordinates of the docking site. But in step 4, we will calculate the exact coordinates of the docking site. The exact coordinates of docking site will also be calculated with the help of Discovery Studio. You can perform the last step for reaching this active site amino acid components. In this case, click on the code of the amino acid to turn it yellow. Then right click and select attributes of ILE 150. You can see the name of the respective amino acid along with XYZ coordinates are displayed here in this label attributes. After clicking on these XYZ coordinates, press this button OK. You have already prepared a list of the active site amino acid. You can see that I have copied the coordinates of valine 13. So click here in front of this amino acid, go to paste and select the first one. Use text imported wizard. Click next, then next again, and then finish. This will paste the 3 values in separate cells. As in the previous step, now go back again to Discovery Studio Visualizer and delete the yellow highlighted amino acid residues by pressing the delete button. Press OK. Now delete this yellow highlighted amino acid which you have just listed. Delete it. Repeat this process for all amino acid in this active site. Deleting the registered amino acid residues will ensure a single entry of each amino acid. After repeating these steps for all amino acids in the active site, I have prepared this list to show you the details of these coordinates. Now add all these values by selecting all the columns and by pressing the auto sum button. You can see that all these values has been added up in this row. Now find the average of these values for each amino acid. How to do this? Click here, enter equal, then click on this value, divide, and then count all these amino acids. These are 18 amino acids, and press enter. Minus 14.2 is the average for all these amino acids. Repeat this formula for all the three columns. The average for y coordinate is 27.45, and for the z coordinate is minus 39.084. You can see here that I have loaded the ligand also to show you how the grid will move to this ligand by entering the calculated values for the grid coordinate. First of all, go to grid box. You can see that the grid box is outside the protein structure. Now I am going to enter the values that we have calculated. The first value is minus 14.214. Minus 14.214. The Y center value is 27.45. You can see that the grid is now moving. The Z center value is minus 39.08. Now let me increase this spacing. So now this grid has enclosed the ligand from all sides. You can reduce the dimensions. So now it's totally enclosed. Go to file and then close saving current. You can also repeat the procedure for saving the coordinates in the text file. Now I'm going to save all these coordinates into the grid parameter file. For creating grid parameter files, go to grid, output, and then click on save GPF. This is your working folder. You can give any name of your choice. There are no rules, and you can give any name that is convenient to you. I am going to give it the name of GP. GP stands for grid parameters. Give an extension of GPF and click save. Now go and check your working folder. You will see that a new file with the name of GP and GPF extension has been created in this folder. The text file grid is also shown here. In the next tutorial, You will learn how to prepare a docking parameter file with extension DPF. The title of that tutorial is You can also reach this tutorial by clicking the link given in the description of this tutorial. Thanks for watching and bye till the next tutorial.